Hey guys, welcome back to Analog Snippets. In last few videos, we have been looking at bandgap circuits as a means of generating rather accurate on-chip voltages. Like any other circuit, bandgaps also have their own sources of errors. So in this video, we will look at some of the more important sources of error in the bandgap circuit and some circuit techniques to minimize those errors. Let's begin with reviewing this bandgap circuit. So we have replaced the diodes by vertical PNP transistors which are ratioed. And here we are assuming that these two branches carry nominally the same current. This amplifier makes sure that the voltage at these two nodes are equal. So basically we have delta VBE across this R1. So let's write down some equations. So delta VBE is Vt ln n, where Vt is Kt over Q, and it's a very accurate PTAT voltage. Currents in these two branches is also PTAT, and it's basically delta VBE over R1. And finally, the bandgap voltage is simply the sum of CTAT voltage, which is VBE1, and voltage drop across this resistor, which is a PTAT voltage. So during design, we adjust R1 and R2 in such a way that CTAT and PTAT slope cancels out and we get a temperature independent voltage. Okay, so let's first consider the process variations in different components. So process variation refers to lot variation in the component parameters. For example, in some lot, a device could be faster than typical, and in some lot, it could be slower than typical. In model libraries, you can usually find slow, fast, and typical device models. Process variation shifts all the device in the given lot by the same amount. So a slow PMOS, for example, means all the PMOS in your design will be slow by the same amount. Okay, now let's take each component in this circuit one by one, and let's see what the process variation in that particular component would mean for the bandgap voltage. Let's first consider PMOS. A process shift in PMOS usually means process shift in its threshold voltage. But MOS threshold voltage doesn't come in this bandgap voltage equation anywhere. In fact, this equation doesn't contain any parameter related to the PMOS. So that seems to indicate that a process shift in PMOS doesn't affect the bandgap voltage at all. Now this may seem strange, but this is actually true. PMOS acts here as a current source. So what matters here is the matching of the current. So what is important is the matching of threshold voltage here, not the absolute value of threshold voltage. Process variation in MOS may also cause the variation in the amplifier gain A. But as long as this amplifier gain is reasonably high, to maintain almost equal voltage at its input, the variation in this gain doesn't make much of the difference to bandgap voltage. So in summary, MOS process variation has very little effect on the bandgap voltage. In fact, bandgap is one of the rare circuits in modern CMOS processes where MOS process variation doesn't play a big role. Here we are specifically talking about the bandgap voltage. MOS does have a role to play when we are talking about minimum supply voltage or noise performance or some other parameters. Okay, now let's consider the resistances. If we consider the bandgap equation, the PTAT voltage contains the ratio of resistances. And that is why if both resistances shift by same amount in percentage, then PTAT voltage remains the same. So here we are talking about voltage across R2. But PTAT current does change with R1. So at fast resistance corner, that means resistance is smaller than nominal, the current will be larger than the typical current. And for the slow resistance corner, the current will be smaller. And since this PTAT current is flowing through the BJTs, the BJT voltage VBE1 changes with the resistance. At fast R, the current will be larger, so VBE voltage will also be slightly larger than the typical. And for the slow R, that means resistance is larger than nominal, the current will be smaller, and hence VBE will also be smaller than typical. And when we add this new CTAT value to the PTAT value, we'll get variation in bandgap voltage. Notice that these type of errors are PTAT in nature, that means as the temperature increases, the deviation from the ideal value also increases. Now since VBE voltage is a logarithmic function of its current, this voltage variation is not a huge amount. Generally the process variation resistance is 10 to 20% around typical, that is on the both direction. And this causes error in VBE which is of the order of a few millivolts. So to summarize, the process variation of resistance have some effect on bandgap voltage, but it has a considerably larger effect on the PTAT current. Okay, now let's consider the process variation in BJT. BJT can also have fast or slow corners. For a given current, a fast BJT will develop smaller VBE across it as compared to the typical BJT, and a slower BJT will have larger voltage. So qualitatively, fast PNP and slow resistance both move the VBE curve in the same direction. Effect of BJT process variation is somewhat more prominent as compared to effect of resistance process variation. And similar to resistance variation, this effect is also a PTAT variation. So the maximum deviation occurs at the highest temperature. At the highest temperature, VBE can differ 10 to 20 millivolt from its nominal value. So in summary, BJT process variation has more effect on bandgap voltage, but it has negligible effect on the PTAT current. Now if we add the effect of process variations of BJTs and resistors, then we can get somewhere around 15 to 25 millivolt error in VBG at the high temperatures. So that is roughly about the error of 1 to 2%. Before we move to the next error source, an interesting observation from this plot. All these different VBE lines seems to converge as we go towards the lower temperatures. Similarly, these Vref lines also seems to converge as we go towards the lower temperatures. If we interpolate all these lines and look at the 0 Kelvin temperature, that is absolute zero temperature, then all these lines will meet at one point. Remember, PTAT voltage will be 0 at 0 Kelvin. So bandgap voltage will simply be equal to the CTAT voltage. That merging point at 0 Kelvin is known as pivot point, and it is roughly equal to the silicon bandgap voltage. This pivot point remains relatively constant in a given process technology. In fact, many times this converging point is used as a test for the accuracy of BJT modeling. So if all these curves do not converge at a single point, that means BJT modeling is not very correct. Okay, so how do we correct these errors? The most common way is trimming. Trimming involves measuring this value on some kind of test equipment and then changing some circuit parameter to correct for the errors. The most common way to do trimming in this circuit would be either changing R1 or R2. In the simplest scheme, R2 may have different tabs towards the top and we simply select the most accurate value. Okay, now let's consider the errors caused by local mismatch. Local mismatch refers to device variation in the same chip. Local mismatch in PMOS refers to different current for the same VGS voltage. In resistance, it means slightly different resistance value even though they are identical resistors. And for PNP, it means that PNP would produce different VBE voltage for the same current value. And in amplifier, mismatch results in offset. Mismatch between R1 and R2 also means a different value of multiplying coefficient for PTAT from chip to chip. Now let's look at most dominant of these effects, which is input referred offset of the amplifier. In fact, BJT mismatch and some part of PMOS mismatch can also be clubbed together with this input referred offset. This input referred offset can be thought of as in series with one of the VBE, and its polarity is not important because it can be either positive or negative because it's a random quantity. Now if we consider every other component to be ideally matched, then this VOS comes in the series with delta VBE. So basically amplifier action equalizes VBE1 with VBE2 plus delta VBE plus offset voltage. So we can basically modify these two equations. So basically this input offset creates an error in PTAT current and in turn it creates error in VBG voltage. Now here we can see why this offset voltage is so problematic. So basically bandgap circuit amplifies this offset by R2 over R1 factor. Now this is a large factor ranging from 10 to 20. So basically we are getting 10 or 20 times amplification in offset voltage. So even 1 millivolt input referred offset can result in 10 to 20 millivolt error in the bandgap voltage. So if we assume offset to be temperature independent, this error simply shifts the bandgap up or down. Now there are some circuit techniques to minimize the effect of this offset. We should of course design a great amplifier with minimum offset. On the top of it, if we could reduce somehow this factor R2 or R1, then also we can reduce the impact of offset voltage. And one way of doing it is basically to maximize the value of Vt ln n. Of course, we cannot change the Vt value by design, so it leaves us with n. Increasing the BJT ratio of n improves the accuracy of bandgap a lot. The minimum value of n that I have seen is 8, and frequently designs use 16 and 24 as well. And in one design I have even seen n of 100, although it's very rare. So what are the limits on n? Apart from obviously area, because larger n will consume more area, it is defined by the limits of the current where the BJT model is very well defined. So if we increase the n for a given value of current, the current in individual BJT finger reduces. On the other hand, if we maintain minimum current in the BJT, then the current in Q1 increases with the increasing N. So consult your device team to know what are the acceptable current extremes in the BJTs. In my experience, on the lower extreme you can go as low as 10 nanoampere, although I have seen design where it has gone even below. And on the higher level it may be tens of microamperes. So basically you've got several orders of magnitude to play with. Another circuit technique to basically entirely remove the mismatch in PMOS is short these two nodes. By doing this, we essentially have one current source on the top of this resistor and BJT stack. Remember, the purpose of these PMOS was to basically maintain equal current in these two branches. In the modified design, this purpose is served by the resistor matching alone, and resistors are much better matched than the PMOSes. On the flip side, shorting these two nodes makes the bandgap startup much more difficult. And this is because shorting these two nodes make the current in these two branches very nearly equal even during the startup. And making the current identical makes the startup much more difficult. In some design during startup these nodes are kept separate, and then once bandgap has started up then these nodes are shorted. On the top of these circuit techniques, trimming is frequently used with the bandgap to remove the error associated with the random mismatch and the process variation as well. An untrimmed bandgap have accuracies to within 3 to 5%, and after trimming this improves to within 1 or 2%. What remains after trimming are error within the trimming circuit itself and some type of temperature dependent error resulting from the process variation, as well as error due to the curvature. Bandgap curvature refers to umbrella shaped temperature plot of bandgap voltage. This is a systematic variation in bandgap voltage resulting from a non-ideal line of VBE. Recall that this negative slope of VBE with temperature results from the exponential dependence of saturation current on the temperature. In reality, that equation is more complicated. This dependence contains additional temperature term which gives rise to this systematic curvature. On the extreme temperature, this value is few millivolts, typically 3 to 4 millivolts. As it is a systematic effect, it can be compensated for. And indeed, many bandgap curvature compensation techniques exist. But it only makes sense to go into those complications once we have got rid of the random errors and errors due to process variations. Now there are techniques to get rid of errors due to offset, for example chopping or dynamic element matching. And then there are various trimming schemes to get rid of the process variations. And then we add the curvature compensation schemes. So designing a high precision bandgap adds altogether a different level of complexity to the circuit. We have now discussed most of the dominant sources of error in the bandgap. I will briefly mention 3 more sources of error which should be considered in every bandgap design. But I will not discuss those in this video in any great detail. And these sources of errors are bandgap PSR, device noise, and stress due to packaging. We can divide the PSR, that is power supply rejection errors, into two categories. Errors due to DC PSR, that is at a lower frequency, and high frequency PSR errors. DC PSR is primarily defined by the amplifier gain, and in a typical design it's easy to get PSR better than 50 to 60 dB. If even higher DC PSRs are required, then basically higher gain in the amplifier is needed. Getting a good high frequency PSR is more difficult problem. One common way to achieve good high frequency PSR is to put a large cap on the bandgap output. I have seen designs where bandgap have even off-chip capacitors of few microfarad. Device noise is another source of error in the bandgap output voltage. There are different types of noise mechanism at work in the different devices. For example, BJTs primarily generate short noise, resistors generate thermal noise, and MOS generate thermal and flicker noise. In some process technology, RTN noise can be a significant source of error. In a fairly typical design, the sigma of integrated noise can be few hundred microvolts. I will cover noise in some more details in a future video. Packaging stress is another source of error in the bandgap circuits. To minimize packaging stress, bandgaps are often put in the center of the chip, that is away from the I/O pad ring, and the bumps or asymmetrical routing is avoided over the bandgap circuits. Okay, so in this video we have covered major sources of error in the bandgap reference generators. We have covered errors due to process variation and mismatch in some details, and I have briefly mentioned PSR, device noise, and packaging stress as some other sources of errors. but not in great details. Hopefully these will be the topic of the future videos, along with some precision techniques such as chopping or dynamic element matching. And this is all for this video. So post your comments below and thanks for watching.